Hello, welcome everyone to the second lecture of the course PH5 BO6 Electrodynamics 2. The contents of this course is taken from Introduction to Electrodynamics by David J. Griffiths. In the last class, we discussed about charges in free space and the field associated with those charges. But in reality, you hardly find a free charge which is sitting idle in vacuum or free space, because we always find charges associated with materials, an electron moving in a copper wire, or charges in your body, right? So charges always reside in materials, so it's imperative that we understand the field associated with those charges sitting inside materials, and also what happens when a material is kept in an electric field. So in today's class, we are going to revise Chapter 4 from Griffiths, Electric Fields in Matter. I am going to talk about two types of materials, namely conductors and dielectrics. We are not going into details of semiconductors because that's an altogether different branch of physics. Now, conductors consist of a large number of free electrons which can move throughout the material. On the other hand, in the case of dielectrics, the charges are tightly bound to each atom or molecule. They cannot move freely throughout the material. They can make certain motion, but that is within the purview of each individual atom. Now, if you want to distort the electron arrangement or the electric distribution within each atom or molecule, you can do that through two mechanisms. One is stretching and another one is rotating, and for this you require an external electric field. Now let's take the most simplest case. I have a single atom, and what's going to happen to that atom when I expose that to an electric field? Let's take the case of a neutral atom. So this is the conventional picture of a neutral atom. It has a positive core with charge plus Q, you can call this as the nucleus, and the negatively charged electron cloud around it, let's say minus Q, is the charge of the electron cloud. So I have equal number of positive charges and negative charges, so they cancel each other. That's why we say this atom is electrically neutral. Now I am going to place this neutral atom in an electric field. Suppose this is the direction of the electric field. What do I mean by direction of electric field? It's the direction in which a unit positive charge moves when placed inside this electric field. So when I say electric field is towards right, that means if I keep a unit positive charge here, it's going to move towards the right. Okay, so neutral atom is kept inside the electric field. What happens? The positively charged nucleus is going to move towards the right, and the negatively charged electron cloud is going to move towards the left. So I have two equal and opposite charges separated by a distance d. This is nothing but an electric dipole, and the dipole moment is given by charge q multiplied by the spatial separation d. Now this is not a normal dipole. This dipole is created solely because I have placed it in an external electric field. So this is dipole induced by an external field. That's why we call it as an induced dipole. Now strength of the dipole moment is proportional to the electric field. I can replace the constant of proportionality with a constant alpha and write dipole moment P equal to alpha E, where alpha is a material constant known as atomic polarizability. Now alpha depends on the microscopic electronic structure, and for different materials we have different electronic structures. Consequently, you have different value of alpha. Now this is the case of neutral atom, and let's now try to understand what happens if the atom has a permanent dipole moment. Let's take the case of a molecule like water. You can see that the hydrogen has a positive charge associated with it, and oxygen being electronegative, it has a negative charge associated with it, which means Whether you have an external electric field or not, water always has a permanent dipole. And such a molecule is known as polar molecule. Now, if you place a polar molecule like water in an electric field, what happens? Assume that this is the direction of the permanent dipole of water and this is the direction of the electric field. Now, the plus Q charge on this side is going to experience a force plus QE towards the right, and the negative charge here is going to experience a force minus QE towards the left. So you have two equal and opposite forces, they cancel each other and the net force is 0, but the net torque is not 0. So the net torque is given by P cross E. As a result of this torque, what happens? This side is going to rotate towards the down and this side is going to rotate towards the up. So you have a clockwise rotation happening, and at the end of the rotation, this permanent dipole gets aligned along the direction of the electric field. Now the energy associated with this dipole is given by minus P dot E. Now let's extend this analysis in the case of a bulk material. Now, a bulk dielectric material consists of a large number of atoms and molecules. When you place this kind of a bulk material in an electric field, all the atoms and molecules are going to respond individually to the external electric field, and if the atoms are neutral, they develop an induced dipole moment in the direction of the electric field. If the atoms or molecules are polar, the permanent dipoles of these atoms and molecules get aligned in the direction of the electric field. So essentially, all the atoms will have dipoles aligned along the direction of the external electric field. Now in this state, I can say that material is completely polarized. So you have dipoles all throughout the material. Now if you take dipole moment per unit volume, this is known as polarization density capital P, or simply polarization, and this is an important parameter to characterize polarization in bulk material system. Now, having understood what is polarization, let's now try to determine what is the field of polarization. Remember, I am not talking about the field which causes the polarization. We call that as external electric field. We want to find out, as a result of polarization, what is the field developed inside the dielectric material. Now you can calculate the potential directly using the Coulomb's law. So you can write potential V of R equal to 1 by 4 pi epsilon naught P by R square R cap, where P is the dipole moment. Now I can write P in terms of the polarization density. So this becomes an integral equation, 1 over 4 pi epsilon naught integral P d tau prime by R square R cap. Now you can do the math and develop this integral and convert one of the volume integrals into surface integral. You get this expression. I am not going into the details of the derivation. So the first term here, it's a surface integral, so this corresponds to potential of a surface charge given by P dot n cap, where n cap is a unit normal vector. Second one is a volume integral, so this corresponds to potential of a volume charge rho given by minus del dot P. Remember, we are talking about dielectric materials, meaning the electrons are not free to move around. They are bound to each individual atom or molecule. So we call this as bound charges, denoted by the subscript B. So sigma B is the surface bound charge and rho B is the volume bound charge. Now what this equation means is that the potential and hence the field of the polarized object is the same as that produced by a volume charge density sigma B plus a surface charge density rho B. Now what's the physical meaning of this surface charge or volume charge? assume that you have a number of electric dipoles arranged along a line, meaning head of one dipole is aligned to tail of the neighboring dipole. So these two charges, the positive and negative charge cancel, these two cancel, these two cancel. So you have all the internal dipoles getting cancelled and charges remain only at the endpoints. So let's quickly look at the case of a three-dimensional object. Suppose you have a cylinder of polarized object. You have dipoles all throughout the material aligned in a particular direction. Now, similar to the case of this line of dipole, all the internal dipoles cancel each other and you have only charges at the end surfaces. So charge divided by surface area will give you a surface charge density here. Since these are bound charges, you have a surface bound charge density here and a surface bound charge density on this side as well. So it's as though we are painting the ends of the cylinder with a surface charge density sigma p. Now this is the case of uniform polarization. Now what happens if the polarization is non-uniform? So in that case, some of the dipoles inside the dielectric, they do not get cancelled. So you have charges within the material as well. And this gives rise to a volume bound charge density rho b. So whenever you have uniform polarization, charges occupy only the end surfaces. So you have a surface bound charge density. Whenever you have a non-uniform polarization, the charges occupy inside of the material as well and you have a volume bound charge density. It's time now to generalize our observations. Now we know that we have two types of charge densities. One, the bound charge density. Second is the free charge density. So the total charge density can be written as rho b plus rho f. Remember the Gauss law, divergence of E equal to rho by epsilon naught. I can rearrange the equation and write epsilon naught divergence of E equal to rho. Rho has two contributions, rho b plus rho f. And we know the expression for rho b, which is minus divergence of P. So I can write epsilon naught divergence of E equal to minus divergence of P plus rho f. Now these two terms have a divergence operator. Let's combine them together and write divergence of epsilon naught E plus P equal to rho f. Now this term epsilon naught E plus P is known as electric displacement or the displacement field B, which describes the displacement effect of electric field on charges within a dielectric material. Now we can simplify the Gauss law. So instead of epsilon naught E plus P, when you write D, you get divergence of D equal to rho f. So this is Gauss law in differential form in the case of dielectric material. You can write the corresponding integral equation. Integral d dot dA equal to QF enclosed, where QF enclosed is the total free charge enclosed by the integrating surface. We can also derive the boundary condition, just like the case of electrostatics, where you saw that the perpendicular component of electric field is discontinuous and parallel component of electric field is continuous. You find that d perpendicular above minus d perpendicular below equal to sigma f, where sigma f is the free surface charge density of the boundary. Similarly, d parallel above minus d parallel below equal to 0. Now, we have seen that the individual dipole moment of atoms or molecule is proportional to electric field. So, in the same way, we can also understand that the total dipole density or the polarization density capital P also will be proportional to the strength of the electric field. Now the proportionality can be replaced by this constant epsilon naught chi E, where chi E is a material parameter known as electric susceptibility. Now we can rewrite the equation for the displacement field in terms of susceptibility. So D equal to epsilon naught E plus P, expand for P, epsilon naught E plus epsilon naught chi E into E. Now let's rearrange the terms and write this is equal to epsilon naught 1 plus chi E into E. Now this term epsilon naught into 1 plus chi E equal to epsilon, which is known as permittivity of the material. Again, this is a material constant. So the expression for displacement field now becomes very simple, D equal to epsilon E. This particular term 1 plus chi E, which is equal to epsilon by epsilon naught, this is known as relative permittivity epsilon R, or a more familiar terminology for this is a dielectric constant. Dielectric constant is a very important parameter, especially in the case of optics, because if you take square root of dielectric constant, you get refractive index. Now, since dielectric constant or permittivity is a material constant, refractive index is also a material constant. For different materials, you have different refractive indices. Now, I have listed dielectric constant for various materials here, and I want to bring your attention to a very intriguing observation here. Look at water. Dielectric constant of water is 80.1. And we also know the refractive index of water is 1.3. Now, if you go by this equation, the square root of 80.1 is almost close to 9. But the refractive index is way lower, it is only 1.3. So, what are we missing here? Now, one important thing I did not tell you so far is that all these parameters, susceptibility, permittivity, dielectric constant, and refractive index, all these are a function of the frequency of electric field. They are frequency dependent function. So let me quickly show a plot of permittivity of a material as a function of frequency of the electric field. Now you can see that the value of the permittivity decreases as you increase the frequency. So here epsilon prime is the real part of the permittivity. Epsilon double prime is the imaginary part of the permittivity. Now, you don't have to bother about these small blips here. So, if you don't consider this, you can see that there is a continuous decrease in the value of the permittivity as you increase the frequency of the field. Now, what is happening here? Let's look at the high frequency regime. So, the field is oscillating very rapidly. So only the tiniest particles in the system, which is the electron, can respond to that fast oscillation. So here, the permittivity has contribution only from electrons. Consequently, the value of permittivity is very low. Now, if you decrease the frequency, now more heavy particles can take part in the oscillation. So you have, in addition to electrons, atoms also oscillating in response to the electric field. So permittivity has contribution from both atoms and electrons, and the value of the permittivity increases. If you decrease the frequency even lower, you have ions and dipoles taking part in the oscillation. So permittivity has contribution from ions plus atoms plus electrons. Consequently, the value of the permittivity is very high. Now, usually when we mention dielectric constant of a material, what we mean is the value of dielectric constant at very low frequencies. This is also known as the DC dielectric constant. So for water, the DC dielectric constant is 80.1. But when we say refractive index, usually the refractive index is associated with light, visible light. So when light passes through water, 1.3 is the refractive index experienced by the light. If you look at the frequency of visible light, it's around 10 to the power 14 Hertz. So we are talking about this region where the contribution to permittivity comes only from electrons. So the value of dielectric constant of water at visible light frequency is very low. It's way lower than 80.1. It's around 1.7, and if you take square root of that, you get 1.3. So I told this entire story to just highlight the point that even though we say dielectric constant or susceptibility is a material constant, so that's partly true for a given material, it's a constant, but when you vary the frequency of the electric field, the value of that material constant is going to change. So that's for today. In the next class, we will revise the chapter magnetostatics. Thank you.